Hello everyone. This will be our last lecture for this course in this semester, and we will end up with some other invariants graph, which measures some kind from different angle of views, how what is the structure of the graph in the larger scale. So first, let's discuss the so-called independence number. So let G be a graph of order n. So a set of vertices U of G is called independent, provided that no two of its vertices are adjacent. And then we can define the independence number, which is a numerical characterization of the subset of G. So independence number of the graph G, denoted by alpha G, is the largest number of vertices in an independent set of G. Okay, or the largest number of vertices that can be colored the same in G, in the sense of the vertex coloring we discussed last time. Okay, in reality, we do have this this problem, because just like in a zoo, so we will ask how many animals can put together at most. For example, if you put a cat and a mouse together, then probably the cat will eat mouse. So it's not a good idea to put together. Then we can have a graphic formulation of this kind of problem. Okay, and by definition, we can easily compute that the independence number for the null graph is the order of the graph, and the independence number of the complete graph is 1. Okay, and similarly, we have another notion of dominating set. So a set W or a subset W of vertices of G is a dominating set if each vertex not in W is adjacent to at least one vertex in W. And then the smallest number of vertices in a dominating set is called the dominating number of G, denoted by dom G. So the dominating number dom G, and here we have the independence number alpha G. And this notion also has a real application, just like in art gallery. Consists of array of corridors and how many guards to protect all, at least. Okay, and we can compute those models, like the dominating number of the null graph is M, and the dominating graph of the complete graph is 1. And here's a theorem which says that if G is a connected graph of order n greater than or equal to 2, then the dominating number of G is less than or equal to n over 2, the floor of n over 2. And geometrically, this can be easily understood that whenever you have two adjacent vertices, you just choose one, and the other one will be dominated. Therefore, on average, you only need half of the vertices. Okay, and the proof, we need to make this clear, this idea more rigorous. So let T be a spanning tree of G. So by the algorithms we introduced before, there's always a spanning tree for a connected graph. Then it's easy to see that the dominating number of G is less than or equal to the dominating number of T. Okay, next, in the following, we consider a tree T of order n. So, and prove by induction. So if n is 2, then one vertex suffices. Dominate T. A dominating number of T is 1, which is the floor of 2 over 2. And now suppose n is at least 3, and let x be a. So if you think about T is a tree, and how to do the induction, we need to truncate T to a bunch of trees with lower orders. Okay, so let x be a pendant vertex of T, and y is adjacent to x, and define a graph T star by removing from T the vertex y and all edges. incident with y. Vertices x and y. Okay, then T star might not be connected anymore. Then we can name the connected components of T star are trees. So this is because it's not trivial, because there's no cycles. And if a connected graph has no cycle, then by the theorem we discussed before, it must be a tree. And at least one of which is a tree of order one. Oh, sorry. Then if in this sense, at the very beginning, we still keep x. Okay, so here x itself is a tree of order 1. Okay, and let T1, T2, Tk be trees of order n1 at least 2, n2 at least 2, nk at least 2. Okay, then n1 plus n2 plus all the way to nk less than or equal to n minus 2. This is because x and y are not in the union of vertices of T1, T2, Tk. Okay, because x is itself is a connected component, and its order is 1, strictly less than 2. Okay, then by induction, Ti has a dominating set Vi of size at most Ni over 2, then V1 union V2 union all the way to UK union Y is a dominating set of T of size 1 plus N1 over 2 floor N2 over 2 floor plus Nk over 2 floor, and less than or equal to 1 plus N minus 2 over 2 floor, which is N over 2 floor. This is found required in the theorem. Okay, next we introduce another invariant. So a clicker in a graph G is a subset U of vertices, each pair of which is adjacent. So in other words, the induced subgraph is complete. Okay, then the largest number of vertices in a clicker is called the clicker number of G, denoted by omega G. So this notion kind of the opposite case for the independent set. For the independent set, you want the edge as fewer as possible, but in this case, you want the edge as many as possible. So here, actually for the model graphs, we can compute the click number. For instance, for the null graph, omega n is 1. For the complete graph, it's n. And as we said, click is kind of a complementary notion of independent set. So how to realize this dual? So we introduce the so-called complementary graph. So here let G be a graph, and then define G bar to be V E bar, where the edge set E bar consisting of all pairs of vertices in V such that the pair is not in E. So you take the complementary of the edge set E as the edge set of G bar. Okay, then for a subset of V, subset U of V, U is an independent set of G if and only if U is a clicker of G hat. And similarly, U is a clicker of G if and only if U is an independent set of G bar. And then in particular, alpha G is omega G bar, and omega G is alpha G bar. So alpha is, recall that alpha is an independent number, omega is a click number. And also, we can formulate the previous theorem that the chromatic number is greater than or equal to the number of the order of the order of a complete subgraph in the graph. So we have chi G, the chromatic number is at least omega G. And then natural question is, what is complementary notion to that of vertex coloring? So the definition: a click partition a graph G is a partition of its vertices into clickers. The smallest number of clickers in a click partition OG is called the clicker partition number. OG denoted by theta G. And by the complementary graph, we can easily conclude that the chromatic number OG is click partition number OG bar, and vice versa. Chi OG bar is theta G. And due to the box here, we have theta G is greater than or equal to alpha G. So a geometrical explanation for this is that two non-adjacent vertices cannot be in the same clicker. Okay, so for an independent set, each vertex should be in a clicker. So the clicker number should be at least the number of, at least the independence number. Okay, by converting a graph to its complementary graph, we can formulate the vertex coloring in the click partition. And then a natural question is, what is the case the equalities in box and the asterisk. Finally, I know how to pronounce this symbol, asterisk. Hold. So to deal with this, we introduce a notion called perfect. So a graph G is called perfect, chi-perfect, provided that chi h is omega h for every induced subgraph HOG, and the graph G is called theta perfect if theta h equals alpha h for every induced subgraph HOG. We are almost doing something abstract nonsense, because it's just what the definition requires. But an interesting and astonishing property proved by Lavar's, which is also conjectured earlier by Burge, is that a graph is chi perfect if and only if it's theta perfect. So this is non-trivial because these two inequalities not exactly the same. They have relations but not so transparent. Okay, so this tells you we can just roughly speaking perfect instead of chi perfect or theta perfect. So remark, we can say perfect graphs instead of chi perfect or theta perfect. Automatically you have these two properties. Okay, next we will give examples of perfect graphs. It's not that trivial for a graph to be perfect because you need to, in principle, you need to test all its subgraphs. Okay, so here we construct several models and then compare some new graphs to our models and see if those new graphs are perfect. So let G be a graph. So a chord or a cycle of G is an edge that joins two non-consecutive vertices of the cycle, and a chord is thus an edge that joins two vertices of the cycle, but that is not itself an edge of the cycle. And a graph is chordal provided that each cycle of length greater than 3 has a chord. If we draw a picture, then you have a cycle and you have an edge between non-adjacent cycles. Non-adjacent vertices in this cycle. Okay. And of course, the chordal, a graph is chordal, is more than just a cycle has a chord. It means every cycle in the graph has a chord. It's a very strong condition. And the example, so Kn is chordal, and tree is chordal. This is tricky because tree don't have any cycle, so automatically it's chordal. And a non-chordal example is given by bipartite. Okay, and for this to be chordal, two vertex in X on the left should be connected, should be adjacent, or two on the right should be adjacent. It's impossible. And to construct, later on we will show that caudal graphs are always perfect graphs. We will not prove that. It's a theorem in your textbook. You can check the details. We don't have time to illustrate everything. And but still, for the caudal graphs, it's still too abstract. We don't have a good way to classify it. So instead, we construct a simpler example. It's called interval graphs. So consider AB as an interval. Let A1 B1, A2 B2, AN BN be a family of closed intervals, and let G be a graph whose set of vertices is I1, I2 all the way to IN, and the two intervals II and IJ are adjacent if and only if they have non-empty intersection. Okay, and then a graph is called a graph of intervals. Such a graph is called a graph of intervals, and any graph isomorphic to it to a graph of intervals is called an interval graph. And then example 1, a complete graph Kn is an interval graph. We can choose to realize it. We can choose A1 less than A2 less than all the way to AN less than BN less than BN minus 1 less all the way to B1. You might have some other ways to realize this relation. It's not unique. And example 2, let G be the graph of order 4 obtained from K4 by removing one edge. Then G is isomorphic to the graph of intervals determined by A4 less than A1 less than A3 less than B4 less than A2 less than B1 B2 B3. And you can check, we have many other ways to realize it. For instance, you can change the row of A2 A3 A2 A4 or whatever. Yeah, I leave it to you to give another model. And the reason we construct a interval graph is because that we can show this is caudal, and then by the next theorem, this is hence a perfect graph. It's in reality, it's not that easy to construct a perfect graph by hand. So that's why we start with some intervals and do some kind of off-topic discussion. So every interval graph is a caudal graph. So let G be an interval graph with intervals I1, I2, In, and suppose that k is strictly greater than 3, and ij1, ij2, ijk, ij1 is a cycle of length k. And we show that at least one of the intervals of the cycles of the cycle has a non-empty intersection with the intervals away from it on the cycle. So in other words, we need to find a chord, and we prove by contradiction assume the opposite, then we can find four consecutive intervals IM, IP, IQ, IR on the cycle for which IM has empty intersection with IQ, and IP has empty intersection with IR. So if you look at a picture, we do have these three edges, but those pink ones do not exist. Okay, then we can summarize. We have three pairs of non-empty intersection and two pairs of empty intersection. The advantage of the interval graphs is that everything is on the interval. It's a one-dimensional thing. So we like a one-dimensional thing. If you think about what is Fourier analysis, Fourier transformation, it's also one-dimensional thing, or transform your high-dimensional objects to one-dimensional stuff. Okay, and if IP less than IQ and BP less than BQ, so graphically you will have AP, BP, AQ, BQ. Then IP is containing IQ, and hence IM intersect IQ contains IM intersect IP, which is non-empty. It's a contradiction. Then either AP less than or equal to AQ, or BP less than or equal to BQ less than or equal to BP. And if we draw pictures, we might have the following 3 examples: AP, BP, AQ, BQ, AP, BP, AQ, BQ, AP, BP, AQ, BQ. Okay, and if AP less than or equal to AQ, then we must have AQ less than or equal to AR. Otherwise, IP intersect IR is non-empty. So we do have this situation. Oh, sorry. This situation. And similarly, if AQ less than or equal to BQ less than or equal to BP, then BR less than or equal to BQ. We have the pink situation, and thus for IP, IQ, IR, we have AP less than or equal to AQ less than or equal to AR, or BR less than or equal to BQ less than or equal to BP. So this is arithmetic. This is arithmetic prime. And here we would like to make a remark that arithmetic and arithmetic prime cannot hold at the same time. Okay. Now, let P equals J1, and first suppose that AJ1 is less than or equal to AJ2. Then iteratively by arithmetic we obtain AJ1 less than or equal to AJ2 less than or equal to all the way to AJK less than or equal to AJ1. And we can thus conclude that all the intervals have the same left endpoint. This is a contradiction because we assume the emptiness of the intersection. So if AJI is greater than AJ2, then we have BJ2 less than or equal to BJ1. In a similar way, we can conclude that all of the intervals have the same right endpoint. It's also a contradiction. So we are done. And I will just state a theorem in a textbook without proof. So every caudal graph is perfect. And the corollary is that every interval graph is perfect. Therefore, we construct a lot of models of perfect graphs. Okay, next we turn to another topic, which is called matching. So a subset M of edges in E is a matching provided that no two of the edges in M have a vertex in common. So the matching M meets a vertex X provided that one of its edges contains the vertex X, and the matching M is called a perfect matching if it meets every vertex. And then whenever we have notion, we can define some invariants. So the matching number of a graph G is the largest number of edges in a matching in G, and is denoted by rho G. A remark, whenever you have some notion, try to find some models in reality. Otherwise, the concept is just like above the sky. It's far from our touching, and we don't have a concrete feeling of it. So how to understand this model, how to realize this model? So first, we can view this as a tournament. You have a lot of players put in a pool, and they pair each other to have a game. Okay, and the rule is that if two players belong to the same team, same club team, they will not compete. Okay, then to have a matching, just like to organize a round of competition. And secondly, you may have some social game. We have a couple of people from different groups coming to a social event, and the people want to know more people, meet more friends, and of course, if they already know each other, they don't need to talk a lot in this event. So they try to match up people who are not occurrent before. And you have a lot of other real case. And then we want to say that this matching number is related to independence number, but you need to change your graph a little bit. So it's called dual version of the dual is not exactly dual version of the independent set. Suppose you have a graph G, and we can construct so-called line graph LG, which consists of a vertex set E and edge set S. So here alpha is an edge if and only if these two share a common vertex in G. And after this, we find that then a matching M in G is an independent set in LG and vice versa. Okay, and the example, so let's compute Kn, the matching number for Kn. So Kn has a perfect matching if and only if n is even. It's not hard to prove this. And in general, the matching number is the floor of n over 2. And another example, a cycle of n vertices has a perfect matching if n is even. So at this case, actually, we have exactly two perfect matchings. When n is even. And in general, the number is also the floor of n over 2. And for a path of n vertices, we also have the matching number is the floor of n over 2. And for complete bipartite graph KMN, so m vertices on the left and m vertices on the right has a perfect matching if and only if m equals n. And in general, the matching number is the minimum of m and n. Okay, next we are going to give another characterization of the matching by the so-called system of distinct representative SDR. And actually for this, in your textbook, we have a whole chapter discussing this, but we don't have time to go over in our course. The whole book is a 1 year long course, but we only have one semester. So I want to introduce the material which I think is the most basic and useful to you. If you have interest, definitely you need to read the textbook or some other materials, as many as you want. And the best way to learn things is always to do some research by yourself. And if you can find some good advisors to start with your research, at least to try something new, then you'll find more deep stuff underneath this course. They have relations, but definitely has more interesting stuff underneath. Yeah, so it's also a philosophical way to state that the world itself is meaningless. Only human beings put some meaning on it. And everything is not that interesting unless we have human efforts on it and show you some structure underneath. Then we can appreciate those interesting stuff. Okay, so the textbook, I think chapter 9 has a lot of stuff on this. Okay, and so we just use the bipartite graphs as an example. So consider general bipartite graphs, and G is V, E. V is V has a bipartition X and Y, and each edge OG has one of its vertices in X and one in Y. So let X be X1, X2, Xn, and Y be Y1, Y2, Ym, and define Kyle AG by A1, A2, An. So this is a family of subsets of Y. So AI is all the Yj such that Xiyj is an edge of G. In other words, AI is a subset of Y, which is adjacent to Xi. And a small remark is that this description actually is equivalent to give a bipartite graph. Just like when we have some Mobius function or the character function or the partial order, it's equivalent to the partial order itself. Given such a family, Kyle AG. Okay, and now suppose E1, E2, En is a system of distinct representatives of the family Kyle AG. So what does this mean? This means that is EI is in AI for all I from 1 to n, and E1, E2, En are distinct. And also this implies that the set M consisting of X1, E1, X2, E2, Xn, En is a set of n edges of G, and no two edges of M have a common vertex. So it's a matching. And we can summarize it as a following theorem. So let G be a bipartite graph as above. Then from a subfamily AI1 AIT OT sets OAG with a system of discrete representatives EI1, EI2 all the way to EIT, we obtain a matching XI1, EI1, XI2, EI2, XIT, EIT, OG, OT edges, and vice versa. If we have a matching, then we can figure out a subfamily with a SDR. And in particular, rho G, the matching number is the largest number of sets in a subfamily of Kyle AG with an SDR. So the reason why we want to formulate the matching number in this way is because that people already have some study of the system of distinct representatives. For example, we have the following very interesting theorem and very deep. For the proof, you can see your textbook. So let Kyle A be a family of subsets of a finite set Y. Okay, let T be a non-negative integer between 0 and n. Then there exists a subfamily of T sets of Kyle A that has an SDR if and only if the cardinality of the union AI1, AI2 all the way to AIK is at least K minus M minus T for all K with K greater than or equal to M minus T and all choices of K distinct indices I1, I2, IK from 1 to all the way to n. So roughly speaking, this theorem just transforms the existence of such nonlinear object that are an SDR to a numerical criteria. You only need to test the number of intersections of a certain subset in this family and apply it in our case. The rho G, the matching number, is a minimal of all the cardinality of the union plus M minus K. asterisk. Okay, and another way to formulate this numerical criterion in a geometric field is use a notation of cover, and we don't have a lot of time to discuss the detail, but I would still like to introduce a notion to you. So a subset W of V is a cover of G, provided that every edge has at least one of its vertices in W. Okay, and then the smallest number of vertices in a cover G is CG. And the reason why cover is useful is because W is a cover, is the same thing as V. Get rid of W is an independent set. Okay, you can easily prove this. And then the asterisk formula, which computes a matching number, can be formulated in the following way. Let G be a bipartite graph. Then the matching number rho G is the same as a cover number CG. This is another version of asterisk formula we gave above. And so we need to make several remarks. First is the theorem does not hold anymore for general graphs. So for general graph, it's more difficult to test the matching numbers. And secondly, we do have some geometric quantity to control this. In general, we use order components, the notion of order components, to describe it. But this is beyond our topic. Okay, I will stop here, and thanks for your cooperation in this semester, and wish you the best in the future, and bye bye, 再见。